Hello everyone, this is Apratim and my teammates Amit Baran Roy and Rahul Sharma, and we have built SFAAS Smart Fetal ECG Acquisition and Analysis System as a part of National Instruments NIYANTRA 2015. As per records, 833.5 million or two-thirds of Indian population still lives in the rural areas which are mostly devoid of sophisticated medical technologies accessible. So, the process of childbirth and the other pregnancy related issues are mostly held by midwives and are hence not accurate and safe. Thus, the infrastructure for pregnant women is very bleak with maternity mortality rate MMR is exponentially higher than the acceptable limits as shown in the figure above. So, we are trying to build an automatic ECG equipment which will separate out the FECG and the MSCG and indicate the defects in the ECG by showing the health of the fetus. The target diseases that will be shown in our equipment is shown in the figure above. That is the consisting of the long QT syndrome, the bradycardia, tachycardia and the Wolff-Parkinson syndrome, the symptoms and the effects for those diseases. So we are using the QT, the BPM and the QRS interval to indicate these diseases in our algorithm on LabVIEW. Next, coming to the block diagram of the system, we have the ECG electrodes coming into the data acquisition device, that is NI-MyRio, and those are filtered and then the abdominal ECG is being acquired. Once that is acquired, it is passed through the feature extractor, that is of the biomedical toolkit of NI, and it goes into the diagnostic palette on the VI, and next this telemetry is being done to indicate the diseases or the non-availability of the diseases in the ECG. Next, we are showing you the setup that can be used for reusable electrodes for acquisition of the ECG. Though this kind of system can be used, but we are more preferable for using scalp electrodes or electrodes that can be directly acquired from the abdomen of the fetus. Next, coming to the amplification circuit, we have used the standard high gain instrumentation amplifier chosen by using the LF353 IC, which has a high common mode rejection ratio. So in this circuit you can see that a gain of 92 is being attained by the circuit and into 3 as the gain of the non-inverting amplifier. So we have a total gain of 276, but this can also be modified by changing the resistor values. Let's move on to the VI.
So now we will show the demonstration of our virtual instruments and how we have connected NI MyRio embedded system device with the LabVIEW and have got our work done. So this is the NI MyRio embedded system device provided by National Instruments. It is a very powerful device. It contains the FPGA processor which can perform operations at a very high speed, and it consists of two ports at the back side, it's port A and B. The port A has the analog channels which can be used to acquire the FECG signals directly from the instrumentation amplifier. Now NI MyRio has this USB host feature which we have currently used to connect the GSM module. The GSM module is essential for our project as it is a part of the biotelemetry. It can be used to send SMS to the patient. Right now we are using this mobile phone to receive the SMS for our simulation. The second part is the Wi-Fi. NI MyRio is like a mini computer. It has USB host feature, a Wi-Fi feature which makes the task very easy. So right now we will enable the Wi-Fi so that we can send emails. So to enable the Wi-Fi, we are using NI Measurement and Automation Explorer. As you can see, the NI MyRio has been detected here. To enable the Wi-Fi, we go to network settings. Right now we are using the Wi-Fi provided by my mobile hotspot. We are connecting it now. So the configuration has been saved and the NIRIO is connected to the Wi-Fi. So this is the setup we are using for the whole process, and we will show you how we do our simulation and perform the further tasks. So this is the previous VI which we have made before using NI MyRio. This was just a simulation based VI. So basically it had everything within itself. So this is the whole front view. The raw ECG, then the filter ECG will appear in these charts, then the diagnostic report and the fetal status. Looking at the block diagram, so there was a prompt input, then the read from measurement file, which will split the signals into respective mother ECG and fetal ECG, and then there is the LMS filter part, which will do the filtering. Then the biomedical toolkit, which we have used to extract the ECG features, and those features will be measured here in this logic. So these are some set points we are using, like for tachycardia, bradycardia, long QT syndrome and Wolff-Parkinson's. Then if everything is normal, a normal SMS would be sent, or if it is abnormal, then the abnormal status will glow. And this is the biotelemetry part, where we have used the SMS of VI and the send email express VI to send the SMS and the email respectively. Now what is the problem we faced is MyRio uses a Linux RT based OS. So basically it cannot run the whole code on itself. So considering the part here, the biomedical toolkit is a separate application which needs to use the processor of the computer. So we cannot dump the whole code together in the MyRio. So what we have used is, we have splitted the program into 4 parts. So we have used MyRio to execute this filtering part, as well as we have used MyRio to execute this biotelemetry part, whereas this prompt user part in the beginning and this one will be used in the PC itself, as well as the biomedical toolkit part. So how to do that? So to run the computer target as well as the MyRio target parallelly, we need to use the concept called network published shared variables. We will see it how it is done. So we open LabVIEW here. We go to the project. So you see, we have used 2 targets. This is the my computer target and this is the MyRio target. So we have created 2 separate files here, the SFAAS_ex.vi and the rio_ex.vi. Both are having the splitted code separately. So we need to execute both the code parallelly For that we are using this shared variable, network published shared variable concept. You can see how it works. So this is the pop-up screen. Here we have to set up all the variables. Currently I have already set up the variables. You can see here these are some of the variables I have set up. So this concept has improved the functioning of both the targets. So we will open both the VIs now. Okay, so you can see this SFAAS-EX VI contains, this is the front panel and this is the block diagram. So basically we have removed the sequence structure from the between. We have used case structures here. These are the variables which we have used. So suppose this starts execution, it will go and store the values in this variable, and this variable will be used in the other VI in the MyRio target. So this is the prompt user input. After we get the input from the user, it is stored in the credentials network shared variable, and after the prompt, the read from measurement file signals reads the LVM ECG FECG file, and the signals get splitted between the AECG and the MECG. And after this sequence has been performed, a boolean flag is stored in the another boolean network variable. So this flag variable will be used in the VI of the MyRio target to start the VI processing in that. And after that, a delay of 10 milliseconds and a 5 milliseconds has been used for executing the biomedical toolkit as well as the next case structure, which is this one. So after we will see the signals here, the MyRio VI will get the control over here, and the LMS filtering part will execute. After this gets executed, we can see the filtered ECG in the front panel. After that, the biomedical toolkit will open, and further processing will take place. And in this final case structure, when it gets true, the prompt feature will again occur, where we have to manually enter the details like heartbeat, QT interval, QRS interval, and sequentially the various logic structures has been used and the set points has been used to compare the values and to detect whether the fetal status is abnormal or normal. And respectively, all these values will get stored in one separate network variable, which will be again used in the MyRio the final case structure when it gets the control over here. So after that, this case structure will execute, and this is basically the biotelemetry part. This is the SMS VI, and this is the send email express VI. So all these values will get transferred to the mobile phone via the SMS and the GSM module, as well as via the email to hospitals as such. So we will look in the final demonstration as how these things together works. So now we are moving on to the last demonstration of our project. We have opened the NIYANTRA project explorer window. So you can see there are two targets, the My Computer and the MyRio. So both will run the specific code parallelly, and before moving on to the code, we need to undeploy the shared library folder. This is to make sure that the buffer gets cleared. And now we are switching on both the VIs. You can see this is the raw ECG VI and this is the Rio VI, which will show the filtered ECG. Here we set the visa resource as the ASRL1 INSTR. This is the port which the GSM module will be using to send the SMS. Now, as you can see, the raw ECG will run on the processor of the my computer and the filtered ECG will run on the processor of the my Rio. We start execution. As you can see, the deployment is in progress and the prompt user for input VI occurs. We enter the name here, followed by the age, and finally the contact number. When we do OK, we see the raw ECG and we start this VI. After deployment, we can see the filtered ECG here, and simultaneously the ECG feature extractor opens. Here we can see the ECG, start the analysis, and we get the statistics here and see the QRS values, the ST values, the heart rate, etc. Now we need to feed in this value to this user input. Let's say we give 99 for the heartbeat, 200 for the QT, 92 for the QRS. We press OK. The values will be executing in that logic block, and we need to stop this VI and restart it so that the shared variables gets updated, and subsequently the SMS and the email will be sent to the respective targets. So we can now check for the email. As you can see, this is the mail which I sent right now, placing on a diagnostic report. This is the name, these are the values we entered, and these are the possible ailments. So this is the detailed report sent to the hospitals, and we simultaneously received the SMS, which you can see here. This is the SMS which we received just now, stating the fetal state is abnormal. Hence, this concludes our project. This is what we have planned to do. So coming to the conclusion, the NIY Rio and the GSM and the Wi-Fi service has helped us to do the biotelemetry and the proper adaptive signal filtering of the ECG. The raw ECG has been applied using the MIT BIH database, and the LVM file is applied at the input of the LMS filtering. The LMS filter converts the file to the TDMS file, and then it filters and removes the baseline wandering noise as well as the power line noise, and gives these filtered values AECG, that is the abdominal ECG, and splitted to give the mother ECG and the fetal ECG. After that, these ECGs are compared with the respective set points which we showed you earlier, and those set points will give whether there is any possible ailments existing, and if it is existing, then the fetal state will not be normal. As you can see here, the abnormal light is on and the data as this is obtained, and the patient will get a SMS, while a detailed diagnostic report, as we saw, will be sent to the hospitals, so further analysis will be required. So this kind of setup is very helpful for areas like villages and other rural areas where cheap medical facilities can be encouraged, so that the health of both the pregnant woman and the fetal can be monitored continuously, and they can be get they can be like monitored for any possible diseases regularly, and their state can be maintained and at a healthy rate.